All right. Hello, everyone. Can I have the attention back? On the back, you guys can hear me or good? So on the good. Good. Better. Thanks for last week attending the class online or watching it later. Then figure out exactly what's happening. But we're back and hopefully we will stay like that. Unless something happens to Jeff. All right. Another one good thing about the COVID time was that we're all equipped with Zoom and stuff and microphone. It was years ago. I had no idea what to do. So let's continue with our discussion with this module, and we'll finish it today. Ready for moving to the more exciting chapter, which is N degree of freedom system. As I promised, if I move back, I post the solution for, let's move back here. Yes, last time, I guess it was on Friday, we get up to example 14. We explained the concept of unbalanced system. I'm not sure if you had a chance to check. I asked you to solve example 14 to 18, and which I also post the solution here as well. Please check the solution, or better, try to solve them yourself. If you couldn't, check my solution, and if you couldn't follow the solution, let me know. Like example 14, super easy. 15, a very good example. Also, it's an important problem. And then example 16, a good practical, like 15 and 16 are good practical engineering, practical problems that you should understand how to solve them. All right, and these are the graphs that we discussed. It's a good summary. Please study that one if you missed the Friday lectures, like this slide. So something different about example 17 is that instead of one excitation force, now we have two excitation forces. Each of them has a different magnitude, like 1000 Newton and 750, but more importantly, they have two different excitation frequencies. How should we solve it? Luckily, we can use the superposition property, and we can pretend that one time the problem is under the first force, but we have the same standard equation. We pretend once that we have this force, we solve it, we will find xt, and the second time we say we have this xt and we add them together. So in other words, if you have several harmonic forces, you still can use the same formula, the exact same formula. You just need to add them up one by one. All right. So, and also I put a MATLAB code there as well. Please check those MATLAB code, because when we get to N degree of freedom, we're going to use MATLAB more, and you better know how to use these MATLAB codes. Not too much coding, actually, it's just plotting for now. And then this is where we say, well, so far this Ft that we discussed, it was all harmonic forces. What if now we have more like a general force, let's say an impulse, or which happens a lot, or maybe just a static force, or any random force. Let's say they're force from a road coming to a car, right? Any general force. There are two methods. One is that this Ft, we convert it to lots of sine and cosine. How can we do that? Fourier series, right? If you remember from your math course, Fourier series, any function, let's say Ft, you can write it as lots of sine and lots of cosine. And those sine and cosine, now you can treat them individually based on what we learn, which is not a very effective way. Better way is numerical solution. For numerical solution, I'm not sure if you had, like in before, use MATLAB to solving ODE, but it is super easy. I just put this example here for you. Please check it. It is on your notebook as well, the step that you need to take to solve an ODE with MATLAB. And coding it in MATLAB is just 4 lines of codes, which again, I put these 4 lines of codes here. The file is on Canvas as well. And please check it. And if you run into any question, let me know. All right. Again, you need these for your experimental tests. You need these for when we get to the NDOF, N degree of freedom system. So you'd better know how to solve an ODE using MATLAB. This is not part of the course for teaching, but it is essential in learning vibration. So on your final exam, you're not going to be tested on this MATLAB code for numerical solution, but for your project, you have a project at the end of next chapter. You need to know how to solve an ODE with MATLAB, which is like easy. It's nothing, right? So, and an example here too also, which I put the code there. Okay. Any question for this? Yes, yes.
For example, 15 and 16, just the idea of balance.
15 and 16. Let's go to 15 and 16. This is 16, right? Okay. So remember when we go back here, we had this topic, unbalanced rotating system. And we said an unbalanced rotating system creates a centrifugal force, which that centrifugal force, because it goes ups and down, it creates some vibration, right, in this example. So now, one is mute. So in practice, let's say we may deal with a motor which is unbalanced, like this example. And as you can see, I applied the same concept. ME omega squared is my mass, unbalanced mass, the force, and I write the equations. In example 16, we are dealing with a car which the tire, on the tire, or maybe not on the tire, maybe in practice it happens maybe more on the wheel. There is an unbalanced mass, but in here, this example, we assume this unbalanced mass is on the tire, MR. So if I look at the side view, this MR, as I highlighted over here, it rotates as the tire rotates, right? So you can visualize this mass is moving ups and down because it rotates around the tire. Yes, please.
So it's the addition of another mass that's
exactly. And but the same concept, the same formula as rotating mass. Please check these examples and again ask me if you couldn't follow the solution. These 3 examples are important. And like this example, after you simplify it, right, let me go over it quickly. All right. So it shows part of a chassis for a car, and like D differential, O is the point that like the whole tire and this assembly can pivot about it, this point O. So we have this tire and then we have this mass mr, which is an unbalance. It is more reasonable to say this mr may be somewhere on the wheel, not on the tire. However, the same solution. So I look at the side view of this tire. So I say this mr rotating around this tire and cause this mr r omega squared force for me, right? So this pink force, now you can visualize this pink force on this picture. Sometimes it is down, sometimes it's up, sometimes it's coming out of the screen, sometimes it's going into the screen, right? This unbalanced force as it rotates, or this mr r omega squared. If I want to show it at this moment on this picture, this is my mr r omega squared. So this force at this moment is down. The next moment it's coming out of the screen. You can visualize it. And next moment is going up. We don't care about when it's coming out of the screen or going into the screen because it causes a vibration for this link, which is, there is no room for that vibration because the way that the whole mechanism works, this chassis can only move ups and down. Like we have only 1 degree of freedom. This chassis can move either up or down. Pivot about point O. So that's why I simplify this problem to a simple problem, as you can see over here. This is my chassis. I have a K and C. I have a force, which this force is mr omega squared sine omega t. This sine omega t takes care of the ups and down force, right? Because sometimes it's positive, sometimes it's negative. Where this omega t came from, similar what we have in the past, because we assume it's going with a constant speed, theta is equal to omega t. And point O is the pivot point. So this problem should be a simple problem and you should be comfortable solving this problem because you've seen this problem before. You write the equation, you ended up with the same exact standard equation that we had before, except your M and C and K and F0 has a different form. I hope that answered your question, or maybe if it was your question as well. But again, I suggest these 3 examples, please spend some time to study them. And example 17, which we talk about it, numerical solution, also important. Please check this one. It is, the whole thing is in your notebook with detailed explanation. And the code, which you can check it, I'm sure you are all familiar with MATLAB. If not with MATLAB, you can use Python or R or other codes that you are comfortable with. So this is just for you as a practice. What is different about this question? Remember in the past, we said when we have a mass, like damping and stiffness, we assume that everything is settled in equilibrium, right? We leave everything to sit at equilibrium, and then we disturb it and we analyze the vibration. But this problem goes like this. I have the mass, all right? Please pay attention for a moment. I have the mass, the spring and damper. I use my hand and hold the mass. So there is no deflection or any compression or tension in a spring. The moment I release this mass, what will happen? There is a shock coming from the weight because I just released these things and the weight of this mass apply a load and that load is going to stay constant. So if I plot let's say the force that I have here, Ft, and this is a function of time, this Ft is a constant force, mg. Right? It's not a harmonic force. At time 0, it jumped to mg and it goes and stay there. It doesn't change its direction, right? This is my Ft now. No other force. So if you write the equation of motion, we will end up with this equation, right? On this side, there is no harmonic force. It's not harmonic, so it means our previous equation that we developed there has no use for us here. So simplify the equation. This is the ODE that we need to solve. We use MATLAB and numerical solution to solve it. If you want your math skill, still you can solve this differential equation. It's not a difficult differential equation to solve. However, if instead of, let's say, this simple ng, you have a more complicated force, then definitely you need numerical solution. Again, please solve this one. Probably if you're taking courses in control, you'll see the response of this system might be something, or maybe let me draw it separately. So the response of this system should be, let's say, jump, coming down, and then settling down at some point. So this is xt, and this is t. But in MATLAB, I put the MATLAB code as well. You can see it exactly where it's settled, which obviously it's settled at equilibrium position. So in control, it matters for us how much it moves up, like what is this jump, how long does it take to settle down, and those sort of things for control. But here in vibration, we just look at the vibration. And I guess you will be the last generation who are taking vibration course in a really traditional and good, let's say, way. Or in future, vibration and control will be a mixed course. And it's going to be, I guess, a 4-credit or 5-credit course, but in a very, let's say, simple way. So you're not going to really get an in-depth knowledge in vibration, nor in control. So try to pass this course this year. And you will definitely. Again, when you take a course with me, those who had courses with me before, you need to try hard to fail. So if you just do the practice problems and the lectures, it will be done. And again, my goal is more than you guys getting a grade, is learn vibration. And believe me, this concept in vibration that I'm breaking down like this one, these are like complicated concepts. I try to simplify them. I teach you in a way that it's easy to understand, and I hope you guys follow this topic easily. You know, my dream of becoming a lecturer or teach at UBC or any university was this course. Like I came to UBC for teaching this course, which took 3 years actually to the system trust me to teach this course. I taught it before somewhere else for a long time. I had a textbook, which is in my office, which I wrote a textbook with lots of problems in it. And but anyway, my point is, please study this material that I give you. These are valuable in future if you are interested in the field of vibration, working in the field of vibration, and even if not, if you're doing other things, still vibration is something. If you recall from the first lecture, I told you something. All the machines vibrates, which means vibration is can be a good business. You can earn good money, right? So here is a new topic, but very easy. We are interested to know how much energy dissipated by a damping. It has a lot of, again, a good application in practice. But let's deal with it quickly and see how we can find out how much energy a damping dissipates or waste in one full cycle. Okay, so this is our goal. We write down the equation of motion, which you know, I'm not going to repeat it. It's going to be mx double dot cx dot plus kx equal to f0 sine omega t. So that's our equation of motion. We managed to solve this equation of motion and find out that xt is x sine omega t plus phi, which we have formula for x and phi. All right. I know the force for damping is cx dot. Right? So I can find then x dot t. And x dot t is going to be x omega cosine omega t plus phi. All right. So I can find out then ft is a function of time, it's changing with time, and it is c omega x cosine omega t plus phi. So that is the magnitude of this force. We don't care about how it changes with time. We care about the magnitude, which is, that's the magnitude. But also I'm interested to see how much energy this thing is wasting. So let's write down energy dissipated or wasted by damper it's equal to the work done by FD. Do you agree with that? So we say the amount of energy that is being dissipated. It's not the wasting is not maybe a right terminology because we want the energy to be dissipated. Otherwise, our system is going to keep vibrating, right? We want to use that energy. So the energy that consumed or used by this damping or by damper is equal to the work that FD is doing. What is FD? Is the force by damping. So to make it simpler for us, let's say in one cycle. In one cycle. Because we know it is vibration. If we know how much energy it wastes in one cycle, then we're good to go. So work done by FD in one cycle, right? So work is equal to the work multiplied by displacement. Since FD is not constant, I have to use integral. FD multiplied by dx. Because at any point, FD is different. So one way is for me to solve this integral, but there is a better solution. Let's look at this xt and fd. Whenever I see a sine and cosine, I'm happy because somehow we can get rid of sine and cosine. I remember when I was in high school, I had a friend and he said, we should be very, very happy. And I said, why? He said, because the square root of sine x, square of sine x and cosine x becomes 1. And I said, why should we be happy? He said, imagine instead of 1, we had like some weird numbers. Then like, let's say 2.1937 or something like pi, right? And then later I learned, yeah, he was right. Because when it is 1, you can do lots of good things about it. Anyway, so now we can use that things and like I have a sine something here, cosine something here. So from equation 1 and 2, I can write down x divided by x squared plus fd divided by c omega squared is equal to 1. All I did, I just write down sine something plus cosine something squared is equal to 1. So you can simplify it and you will get to this equation. So what is this equation? Looks like a circle or no? Looks like an ellipse. Do you agree? So let's see. Gonna draw an ellipse here. So ellipse, if I have, let's say this is y, this is x. Remember, we had like x squared divided by a squared. Let's say this distance is a. And let's say this distance is b. So this is b, this is a. Then I can write down x squared over a2, y squared over b2 is equal to 1. That's the equation for an ellipse, right? So the same here, we have an equation for an ellipse. So in other words, I can plot FD, the force in damping, as position displacement. So it will be an ellipse, which in this ellipse, this distance will be, let's so this distance will be, this is on x, it is x, and this distance will be c omega x. All right? Yes.
Do x and b squared.
Oh, they have to be square. X. Yep. We squared them, right? We squared them, so we could write this one. So do you guys agree? This is a, yes, please.
The x's in that first, that are both the same x.
This one the same x, right? This, you mean this one and this one?
And the one on the the first term of the ellipse.
Okay, no, this is something is a variable, it's change. This is variable, right? It changed, and FD also is a variable. They change. So FD and X, they change, but this is a constant, right? Remember, this X is the same X as amplitude of our vibration. This is X also, all right? I'm going to give you a moment, think about it, and see if you follow what happened, right? This is in fact very simple. We have the equation xt. What is the force in damping? We know it is force in damping is damping multiplied by a speed. So I take the derivative of x dot. So this is my equation for FD. From 1 and 2, I managed to get like this equation. So x and FD, they are changing. They are a function of time and position, and they change. This is X. But capital X, like this capital letter X, is a constant force. C is a constant, omega is constant. So this is an equation for an oval, right? And what this integral means, let me delete that things. And maybe I move that things down over here. Just gonna make some rooms for myself. And all right. So we managed to find that energy by damping is equal to FD dx. So do you agree that this is equal to the area of the FDX graph? This integral is equal to this area, and this area we know how much it is, right? For an ellipse, I write it down up here. For an ellipse, the area of the ellipse, who remembers the formula? It is I A B, right? So it's going to be pi AB, which here is going to be C omega x squared. So let's show this one by W damping, means work done by the damping. So from this slide, I want you to take away two things. One, in one cycle, this is the amount of energy dissipated by the damping. Again, an important formula, people in practice also use it a lot. This is the amount of energy that goes out, dissipate by the damping, pi, c, omega, and x squared. This x is again the capital X, the amplitude of the vibration. It's not a function of time. It is in one cycle. The second thing is force in a damping change with x, with the position in this ellipse form. And this is how the force Fd as a function of x change, as I graph it over. This is their relation. So how people use this one in practice, people put like a sensor let's say a sensor, they put a sensor, a force sensor on the damping. This can be a very simple force sensor. It measures the load, the tension in this damping for us. So they measure the force. They also put a sensor to measure X. So they can measure the force in a damping and the position. That's easy to measure. Displacement sensor can tell us where we are. So we have FD, we have X, and then they plot these two and look at the graphs. So these are examples of graphs in practice. This is for a shock absorber for a bus, like a city bus, and this is for like a passenger car, a small car, maybe a Toyota Corona or something like that. Corolla, or maybe a small car, anyway, it doesn't matter. So the graph, they don't look like an ellipse, right? They close, more like a marshmallow or a very ugly egg. But this is practice. So in theory, we expect to see this nice oval shape or ellipse shape. In practice, we don't get that one. So these are two different graphs, and like this is for one of them. I just put both in one graph. And the other one is for the small car. So these two, they go the same length of, you can see the same length, but their force is different. Their amplitude of their force is different. Anyway, so when they do this test, they let the damping to warm up. Because remember, inside this damping, there is oil. So at the beginning, when you do the test, you are not going to get this nice graph. So they let it to warm up after 10 minutes. The oil is warm enough. Their viscosity is stable because remember the viscosity of oil changes. And because there is friction, of course, it's going to heat up, the oil warm up and everything settle down. So then they measure force and displacement and they get this graph. What they use this graph for? Well, they do this test a lot to measure like the area inside these. If they know the area inside that one, right? If they know the area, they know X. So they have this WD, they know X, right? X from this graph, you can find out what is X. So like from here to here is 2X. And that's the amplitude of vibration. So then they can estimate the damping C, the damping coefficient for this shock absorber to compare it with what the factory claim. And usually they do this test every once in a while because the damping coefficient is changing. After, let's say, your car, after 1 or 2 years, of course, the damping is not going to be as like new, the damping changed, so they need to check to make sure there is any issue with the damping or not. So that's it. Any question for this one? So it means if you go somewhere, work for a factory that produce dampers, which in fact, they are nice factories. I've been in one that produce damping, and it's quite advanced and complicated. It's not like that easy that you think they're making this damping. Of course, they're making their cylinder and the piston and the oil, but all the test equipment, it's like fascinating. So if somebody gives you this graph, first thing you do, you find the area of inside that graph. It gives you WD. What is WD? The work done by dampers in one complete cycle, or the energy dissipated by the damping. And you have the cycle of vibration, X, so you can estimate the damping coefficient. Also, you can compare that number to make sure if they are matched with over here as well. Because the distance over here, you know, it has to be, don't forget that 2, this is 2C omega X, right? Remember our original equation, this is X over here, and this is CWX. Any question for this? Yes, Ahmad.
We wanted to see the work done by the damper on not the initial cycle. When we plug in like the logarithmic decay, I think we know we can dx. This question.
Okay, so you're asking if if you don't want to know what happened initially? Yes, yeah. That's why we go for the steady state. That's why we go with the capital X. Right. Like we don't care about the initial few seconds that whatever the response is. Right? So in vibration, the steady state response is what we focus. And the same, yes, we don't care about the initial few seconds, whatever energy is. All right, so, and this is the last topic, which is a very short topic, dry damping. So remember, damping can be one of these three sources. It can be a viscous damping, which is what we discussed so far. This is something that intentionally we create. We put damping for cars because we want to remove vibration. Right? So those are viscous damping. It has oil inside and they have these coefficients C. Two other dampings, one is air resistance, like in air, because of air resistance, that acts as damping. And another one is friction. Those are maybe unwanted, but they are there and they reduce vibration because they waste energy. Air, we don't care about air that much because again, the damping effect of air is not really that much. Water, yes, it is, but air, no. Friction, like a static friction, dynamic friction, or dry friction, that is a source of damping. All you need to do to know about the dry damping is whatever we are going to have in this slide for the next 7 minutes, and not more than that, because the focus of vibration is more for the viscous damping, what we had before. So, like always, I need to draw the free body diagrams to write the equation of motion and solve these things, right? So if I draw the equation of motion, of course, we need to start with the free body diagram. I'm going to have a force here, which is Kx. Imagine that you disturb it by x, right? And I'm going to have friction, which friction is the opposite direction of x. So remember, this is what we selected, and we said that the mass is moving toward x, the spring is going to apply kx, and here is going to be mu n. What is n? Obviously, n is the normal force. In this scenario, of course, n is mg, but let's keep it as n because you may solve in future another problem which n is something else. Maybe if I apply a load on top of this mass, right? So whatever n we have. So that's our free body diagram. Newton can help us here. Some of the force is ma. So I end up with mx double dot plus kx equal to mu n. That's my differential equation. It's not harmonic. So one way to solve it is, of course, numerical, but we can attempt to solve it like analytically. So since it's not equal to 0, my xt has to have two responses. One is particular response, one is the complementary response. The same drill that you know. xp, I need to guess an answer, right? When I have mu n. So the only function that I can see fit for xp particular solution is going to be mu n divided by k. See, if I put this xp in these two equations, the first one becomes 0, and then the two sides of equations are the same. For my xc, I go with a guess of a cosine omega nt plus b sine omega nt. Again, we will guess and see how it works. Of course, I know in advance, that's why I write this one. So something that you need to pay attention. We have omega n here, not omega, right? Because there is no excitation frequency or a force with an omega. So that's why I had to write down omega n here. Or I might be wrong, so it should be something else. But omega n is the correct answer. A and B, they are what we need from initial condition. Let's say, just for the sake of discussion, we have initial condition of x 0, let's say at t equal to 0, x0, and let's say v0 is equal to 0, just for simplicity. I don't want a long equation. So it gives me xt equal to x0 minus mu n divided by k cosine omega nt plus mu n divided by k. So that's the answer to the differential equation. Where it comes from? Well, we have xp, we have xc, we add these two because xt is sum of these two, right? And we have our initial conditions. You can also include v0 later for yourself, but you get a longer equations, which is not suitable for what I want to discuss in a moment. So now in this equation, take a look at, we have x0 minus a value here and then cosine omega nt. We want to know, remember in viscous damping, the amplitude of vibration becomes slower and slower and slower until it gets to 0. Not slower, smaller and smaller until it gets to 0. We want to know if some similar things happens here or no. If I disturb this system by x0, it's going to vibrate forever by x0, which intuitively we know it's not going to happen because we have friction. So somehow the vibration has to get smaller and smaller and gets to 0. But how much? So let's say, I'll be done in a moment here. This is our initial condition, right? I move this box by x0. So I'm here. Let's say this is x0. I want to know if it returns back, how much it will move back over there. That one, it's better. Okay, so I know the distance from here to here is x0. I wish to find out what is this distance. So all I need to do is from this point to this point, the system finish half cycle. We agree? Remember, a full cycle is going there and coming back to original, not original, to this x0. So over here is half cycle. And half cycle means omega nt equal to pi, right? Remember, our cycle is being controlled by omega nt. The full cycle for a cosine is 2 pi, and now half cycle is when omega nt is equal to pi. So if I put that one there, I would get this distance minus x0 minus 2 mu n divided by k. Just put omega nt equal to pi in this equation. It gets -1, and it gives you that value. So what it tells us that you got from x0 to x0 minus this number. So it means definitely the amplitude becomes smaller. So it's not going to stay forever. When you have friction, when you disturb it, the amplitude becomes smaller and smaller. How much smaller? In half a cycle, 2 mu n divided by k. So, and what it tells us, it means it's a linear decrease, because I was x0 and I get x0 minus this number. So I'm going to write down here then the amplitude reduces linearly in each cycle or in each half cycle by 2 mu n divided by k, or in a full cycle by 4 mu n divided by k. Why 4? Because now it's linear, right? So if I quickly plot these things, time is passing, so I'm almost done. Unlike the other one, the amplitude decrease is linear. So over here it is x0, but the amplitude of this one is 4 mu n divided by k is less. That's all we need for the dry damping. Okay. So definitely when we have friction, the amplitude decrease. How much? In each cycle, 4 mu n divided by k, and it is linear. Thank you very much for listening. I'll see you on Wednesday. We start the n degree of freedom system. Try not to miss the lecture for Wednesday. Thank you, guys.